So my name is Kirit Thadaka. I'm going to talk about NumPy, and I hope by the end of this, everyone learns some cool tricks and has a lot more of an easy time with computation in Python. Has everyone cloned the GitHub repository? If you haven't, this is the link. It has the notebooks that I'm going to be using for this tutorial. So if you want, just go ahead, clone it, and then you can follow along with the rest of the tutorial. Everyone can see this just fine, right? If anyone needs me to zoom it further, please let me know. Otherwise, I'll go ahead. Yeah, okay. More? All good? Okay. Has everyone got the notebook, or should I wait for a couple more minutes before everyone's ready? All good? Cool. So to start off with, let me give you a very short introduction to NumPy. NumPy, or numerical Python, is Python's premier scientific, mathematical, and computation library. It's got a lot of highly optimized functions in it to do, some hardcore math, which makes it a lot easier if you're using code that relies on efficient performance. It's a lot of number crunching, and if you need things fast, then NumPy is the best way to do that. As we know, traditionally Python is a fairly slow language, and it may not be useful for all your use cases because sometimes you need speed, and when you need speed, NumPy is a really good way to get it. So having said that, I'm going to dive right into the notebooks, and as we go through the notebook, I'll talk about different parts of NumPy, and hopefully you guys can understand where you can use NumPy in the work that you do. And if anyone has any questions during the tutorial, please feel free to raise your hand, stop me, and I'm happy to answer whatever questions you have. So to start off with, first thing we do is we have to import NumPy. So that's what I've started off with in my notebook. Now the core foundational data structure in NumPy is the array. And I'm just going to start out with some examples of how you can create a NumPy array. There are many different ways to do it. One is using this syntax np.array, you pass in a list of whatever elements you want. Here I've passed in a list of 2, 4, and 6. And then A now becomes a NumPy array. And there you go, that's A. You can also create a NumPy array using the function ones. In this case, what you pass into it is a tuple that represents the shape of the output array that you want to create, filling all the elements with 1. So here, if I want an array that has 2 rows and 3 columns and all elements in it to be 1, I can use this function np.ones, pass in 2, 3 to it, and it gives me an array of all ones, just like this. Here it takes the default as the data type default as float, which is why you see 1 point and 1 point all over. I can also pass in the data type that I want here using the dtype parameter. And here it creates a NumPy array of ones where the data type is an integer. I can do the same thing with the np.zeros function. Again, here I've passed in the shape as 3, 2. So I want 3 rows and 2 columns in my output array. All elements should be 0, and that's how I get it. NumPy has a function arange, which is similar to Python's range function, except this is not a generator. It actually creates a list of elements from the start and stop point of your range. So here the function I've written is np.arange of 10. So I haven't passed in a start, stop, and a step. I've just said 10. So by default, it assumes the start to be 0. It takes 10 as the end, and it creates a list with the range 0 to 9. And that's what you get over here. So now I have a NumPy array of elements 0 to 9. 2 more cool functions are tile and repeat. What tile does is it takes the first argument, in this case it's 2, and it tiles it together in the shape passed as the second argument. In this case, it's 5, 3. So that means this function will take the element 2 and replicate it so that it reaches the shape 5, 3. So in this case, you now have an array with 5 rows and 3 columns, each of the element 2. What I can also do here is, instead of 2, which is just an integer, I can pass in another NumPy array. I can pass in a list. So let's try passing in what I created before. So if I take tile, pass in np.arange of 10, and say the shape, output shape I want is 5, 3, this is what it does. As you can see here, along the columns, it's repeated the sequence 0 to 9 3 times, because that's the number of columns I specified in the second argument of the tile function. It's taken the list and replicated it 5 times on the rows, which is why we have 5 rows of this sequence of 30 numbers. So that's what the tile function does. Repeat is similar, except it takes whatever you pass in as the first argument and simply repeats it linearly, specified by the number of times specified by the second argument. So in this case, it takes the list 1, 2 and just repeats the list linearly 5 times. So here it takes each element of the list and repeats it the number of times specified by the second argument. So here I pass in the list 1, 2, and unlike tile, it doesn't take the entire list and repeat it. It takes each element and repeats it based on what you specify in the second argument. So which is why we have 1 5 times followed by 2 5 times. So that's the difference between tile and repeat. Now this function linspace, what you can do with this is specify a start to the range you want, an end to the range you want, and the number of elements you want within that range. So with this function, what I'm doing is I'm specifying that I want my sequence to start with 1, I want it to end with 5, and I want 10 equidistant points within that range. So it calculates what delta should be added to each number to create an equidistant set of numbers between 1 and 10. Oh, sorry, 1 and 5, and 10 such numbers. Is everyone good so far? Does anyone have any questions? Okay. Now the np.matrix function can be used to create a matrix instead of creating with a different syntax than you would have used if you used the numpy.array function. So here, I personally don't like this method of creating an array, because I would rather just use np.array and pass in a 2-dimensional list to it. I feel it's more intuitive, it's more likely to be what you use through your general programming. I've used NumPy for a long time, and I've pretty much never used the matrix function. So to me, it's a pretty useless function, but I just thought I'd put it in here anyway so that everyone knows that this is an option that exists. Not sure why you take that option, but it exists. So this is the way you would specify that. So along the rows you have 1 and 2, and on the next row you have 3 and 4, and you create a matrix that way. If anyone finds a compelling use case to do this, please tell me.
Okay. So if you have a text file that you got on your hard drive and you just want to read it in and make it a matrix without having to convert all the text into numbers, you can just pass the string straight into it.
Yeah, but you could also just do NumPy from txt or something, right? Yeah. That's obviously a useful use case, but I meant if you were like writing code where you weren't taking it from a text file, then I wouldn't use this. But yeah, I have to agree, that does work. You can also create a structured array in NumPy. So in this case, here I have, so here I have a structured array where I have labels and I have probabilities as the 2 data types that I want to store in my array. So I've called the 2 labels that I have A and B, and the 2 what I've called as probabilities, which are float values as 0.8 and 0.2. Now, the first part is similar to the numpy.array syntax, except here you're passing data types of different categories. And in the D type is where you specify the labels that you want each of these to represent. So in this case, the first value of the tuple, this tuple, the first value is a label, which is why I specify that over here. And A8 means it's a string, a character. And then the second value of the tuple, which is 0.8, I've defined as probability, or PROB, and I've specified the type as a float. Now, when I want to extract elements from my array, I can extract it through the label that I've given. So here I can say x of label, and it gives me A and B as the two labels that I have in this structured array. And if I do x of prob, it gives me 0.8 and 0.2, because these are all the elements in my NumPy array labeled as probability. So if you have a larger set of data and you want to get all the values that you've defined by a particular label, you can index the array, pass in that label, and then retrieve everything that is of that particular label. So that's how you can achieve the structured array functionality in NumPy. Now, that was the basic stuff, how to create an array, some of the basic things you can do with NumPy arrays. Now, to get to some of the cool parts of NumPy, and the coolest by far and the most powerful part of NumPy is its broadcasting ability, and that is really what makes NumPy very easy to use. It makes it efficient to use, and it just overall improves the programming experience. So here, if I have two arrays, A and B, each with 3 elements in it, and I wanted to do any operation on the two of them together. So for example, let's say I wanted to add these two arrays together. Now, if I was doing this in, for example, C, I would take the two arrays, I would write a for loop, I would iterate from 0 to 2, add each element together, store it in an output array, which is fine. That's cool. C is fast, so we can do that. In Python, loops are not your friend. Loops make things really slow, and you want to avoid loops as much as possible. So taking these two arrays, looping over it, in a case of 3 elements, fine, doesn't make a big deal. But if this was 3,000 elements, you would not want to be looping over 2 lists to add them together. With NumPy, you have the ability to add these 2 lists together, and internally, what it does, it broadcasts this operation across all the elements of the list. So now the addition operator is broadcasted to the first value in each of the arrays that I have, to the second and to the third, to add all of them together in what we see as one operation. So let me go ahead and define this. Now if I want to add these two together in one operation, I'm able to add element by element the 2 arrays that I've just created. Whereas without this broadcasting ability, if these were 2 Python lists that I wanted to add, you'd have to iterate over each of the lists and add them together and store it in a third output array. Now what's really cool is, in the next case, I take the array A, which has 3 elements in it, and on the other side of the plus, I have a 1. It's not an array, but I want to add 1 to each element of my NumPy array. What broadcasting does here is it takes the integer 1, it treats it as if it was an array of 3 ones, because it sees that on the left hand side of the operator, the dimension of the array is of length 3. So it broadcasts the 1, internally makes it an array of 3, and then does an element by element addition of the 2. So in this case, I take the array A, add 1 to it, and each element is incremented by 1. And that's possible because of broadcasting. And the same way, I can do it for all of these operators. For A minus 9 subtracts 9 from each of these elements, and the same, if I multiply it by 10, it multiplies each of the elements in my array by 10. Now with broadcasting, there are particular rules that you need to be aware of to identify whether something will follow broadcasting or whether it won't. And for that, it's a pretty simple rule. You look at each dimension of your NumPy array, and for two arrays to facilitate broadcasting, at each dimension, they should either be equal or one of the dimensions should be 1. So for example, in the case over here, both of these arrays have the same exact dimension. So broadcasting would work. In the case over here, you have A and 1. 1 is treated as a dimension of length 1 and A has a dimension of length 3, in which case it still follows the rules of broadcasting because one of the two is 1. So that's what you always need to be aware of. Either the dimension should be equal or one of the arrays the dimension should be 1. So in the case of these two arrays over here, if I want to add them, then I know that the dimension of my first array is 20 by 5. The dimension of my second array is 20 by 1. So now I want to check whether these two can be whether broadcasting will take place in this case or not. So I start from the right and I look at the second dimension, and in the array A, the value is 5. In the array B, the value is 1. So that checks out because one of them is 1. Now I go to the left and I see it's 20, the first dimension of A. The first dimension of B is also 20. Again, it checks out because both are equal. Now in this case, I know broadcasting can take place, which is why when I add it, it's all good. The NumPy arrays get added. So now let me ask you, will these two NumPy arrays, will it work if I add them two together? Can they be broadcasted? Does anyone think they can't be? Okay, so everyone thinks they can be? Okay, let's check. Are you sure no one wants to change their mind? Okay, cool. And yeah, they can be added together, and that's because at each dimension, the dimensions are either equal or one of them was 1. How about this? Show of hands for yes, they can be, broadcasting will take place. Okay, anyone for no? Okay, you think they won't be broadcasted? No, sorry. Oh, okay, this one. And yeah, they can be broadcasted. Okay, and now for the next one, does anyone think they can't be broadcasted? This is the one that you said you don't. Yeah, does anyone think they will be broadcasted, these two arrays? Anyone still not sure? Yes, no, or not sure? Okay. Cool. Let's try it out then. And no, they couldn't be. And that's because when you look at these two arrays over here, the first one its dimensions are 9, 1, and 2. And the second one, the dimensions are 1, 9, and 8. So when you start from the right side, you see the last dimension of A is 2, and the last dimension of B is 8. And the rules of broadcasting say that the dimensions should either be equal or one of them should be 1. So this violates that because they're neither equal and neither of them is 1, which is why they can't be broadcasted. In all of the previous cases, the dimension was either equal or one of them was 1, which is why it worked. Now another really cool feature with NumPy is the ability to index into arrays in many different ways. So again, starting with just an random array, an array of 0 to 24. The colon operator is used as the indexing operator. So when I index into an array like this, what I'm telling it is, on the rows, I'm just passing in a colon, which means I want everything. There's no start defined and there's no stop defined. So ideally in the colon, the syntax is on the left-hand side of the colon, you have the start. On the right-hand side of the colon, you have the stop. If neither is specified, it defaults to just 0 to end. So which is why on the rows, now everything is going to be returned to me. and np.new axis is used to create a new axis. If you look at the array A, there's only one, it's a one-dimensional array, right? So if you were to check out the shape of A, it's just 25 comma nothing because it's one dimension. Now when I use this syntax to index into the array and I pass in colon comma np.new axis, what I'm saying is take the array A, give me all the rows and add a new dimension to it after that. So now it takes this array and it creates an artificial second dimension. So now the shape of this array becomes 25 comma 1 because the new axis has been inserted into that array through the np.new axis function. Here I'm not storing it in another variable, which is why in the subsequent examples it won't retain the shape 25 comma 1, but it's a way that you could use this to reshape an array, you could use this to just add a new axis for whatever you're doing. In some cases, for example, if you're using Keras, for example, and you pass in any input data set to it, sometimes it requires you to have the last dimension as 1, in which case you could just use np.new axis, pass in the array, and then your downstream computation would be fine.
So is it on line 29 the dimension is not specified?
Sorry?
On the line 29,
On
the dimension of the array is not defined?
No, so when I do np.arange of 25, it returns an array of length 25, right? So it's a one-dimensional array. So here when I print the shape of A, it's 25 comma nothing, right? Because there's only one dimension. It's a one-dimensional array, right? It's a linear thing. But now when I pass in the second line on line 31, when I say np.new axis, I'm taking this one-dimensional array of length 25 and making it a two-dimensional array of 25 rows and one column, which is why if you print this, it's 25 rows and each row has one element, right? So now it's essentially a two-dimensional array. That second dimension is introduced through the np.new axis function in the operator, in the indexing operator, in the square brackets. Yeah. So now here I've created an array of numbers from 0 to 24, and I've reshaped it to the shape 5 comma 5 comma 1. So it has 5 rows, 5 columns, and each element has its own artificial third dimension to it. So if you look at the shape, it is 5 comma 5 comma 1, which is what we specified. No surprises there. Now another neat indexing operator is the ellipsis, which are these 3 dots you see over here. So now in this line what I've done is I've said I want from the array A, which is now 3-dimensional, 5 comma 5 comma 1, give me the first row and everything after that. That's what this ellipsis does. It says everything that is left from all the other dimensions should be returned to me, and that's what the ellipsis is. So here, if you look at the output, you get the first row and you get 5, 6, 7, 8, 9 retained in the square brackets because the next axis is 5 comma 1. And on the next line over here, it's the same thing. So you can see that the 3 dots, the ellipsis function, translates to the colon operator in all remaining dimensions. So if I had my array shape as 5 comma 5 comma 5 comma 5 comma 5 for however long I wanted, and I said I want the first row of this, and I don't want to specify that I want everything from all the other dimensions, I can just do A of 1 comma dot dot dot, and that would translate to A of 1 comma colon comma colon comma colon comma colon for however long I've specified my dimensions to be. So it's an easier way to access and index through your entire NumPy array. Now, as we see from this array A, there is clearly one dimension that is very unnecessary, which is the last one. In this case right here, it's not really serving a purpose for us. And many times when you're getting inputs coming from different functions or different processes, you may receive data that is shaped similarly, and for your downstream processes, you may not require having the data shaped like this with the third dimension or an nth dimension with just one element in it. And there may be many cases where you have many dimensions that are just one. For example, in one of the broadcasting examples that I put up, you have this array which is 9, 1, 1. Now, if I just want to treat that as a linear array of 9 elements because the other 2 dimensions for me aren't really serving a purpose, I can use the squeeze function, which essentially returns a new array to me with all dimensions that were just 1 removed. So in this case, now anyone want to guess what the shape of A is going to be? By the way, A was 5, 5, 1. So now after running the squeeze function, any guesses what the resulting shape of A is going to be? I have a cookie for anyone who answers. I brought one from outside. Yeah. Okay. Yeah, okay, so who gets the cookie now? If you guys want to share, go for it. Otherwise, there are more questions later and we can give the cookie to someone who answers that. And he's got chocolates as well. So now this is the new value of A, so that... You want the cookie? Sure, go for it. No, I brought this to give someone who answers the question. There you go. So here, if I want, for some odd reason, after I do all of this to get my array back to being 5, 5 and removing that dimension, if I want to, for some reason, bring that dimension back, then I can do this and index my first and second dimension using the colon. So I'm saying I want everything from the first and second dimension. And for some reason, I now want this third dimension again. So I use the np.new axis. And we're back to the original array. Another thing you can do while indexing is you can pass in lists to the row and column instead of just a range through the colon operator. Instead of saying a start and end, you can pass in discrete values of which rows and which columns you want to return from your array. So in this case, just take a minute, and in the array that you see above right here, if this is what I passed to it, this would have been a good question to give her a cookie for. Yeah. Anyway, no worries. Anyone want to take a guess as to what the output of this line here would be? If I'm indexing my array with, if this is how I index my array, the first list is being passed as the row indexer, the second list is the column indexer. What would the output be?
First 5 items of the diagonal of your matrix.
Okay, so the 5 items of the diagonal. Does anyone think that that's wrong? Does anyone think that you'd see something else, or does everyone agree with him? Yeah?
I don't know what it does.
Okay. It gives back the original array? Okay, so we have 2 guesses. One is the original, one is the diagonal. Anyone else? Yeah.
1, 2, it would be 1 row.
Okay. So we got 3 different answers, and whoever gets it right gets a chocolate from him. And what we get is, in fact, the diagonal. Yeah. And that's because think of it this way. So now I've passed in a list over here to the rows and a list to the column. And what it does is it takes row 0, column 0, row 1, column 1, row 2, column 2, row 3, column 3, row 4, and column 4. and that would result in getting the exact elements along the diagonal of the array.
Is a linear way to access the diagonal elements?
Sorry?
Is a linear way to access the diagonal elements?
Oh yeah, there are much cleaner ways to access the. This is not how you want to be accessing the diagonal at all. I will come to the much better ways to do it. This is just an example of how you can possibly index into a NumPy array. Yeah.
So this is purely theoretical because I don't think there would be a reason why you'd want to do this. But like, let's say you wanted, instead of just getting the diagonal, you wanted to have it like iterate through each one. So like have it 0, 0, 0, 1, 0, 2. Is like the way to do that using the colons, or?
I'm sorry, I didn't fully understand. What output are you saying you want to see?
Like almost just basically like the same array, right? But like to have it, because you're only pulling out like individual ones with the diagonal.
Yeah.
Using like the input of list, if we wanted to run a list but have it be the entire, like everything in the row.
Wait.
So almost like
diagonal, only the diagonal and zeros everywhere else? Is that what
no,
you're
no, no,
asking
no.
for?
Like so, that's what I'm saying is like purely like theoretically,
Yeah.
because there wouldn't, but like to reprint it, because right now like because you have it as two lists, it's taking like the 0.
Oh, okay. So you wanna basically
Yeah.
So the output should be the original
Right.
array, but the method I use to get it should be similar to this, right? Like passing in two things. Okay. Okay, we can try that. Cool.
If you make either of those lists that you pass in into a colon, it should do that.
Right. I think
Yeah.
it would just be like colon.
Cool. So we can try it. So what do you what do you think it should be?
So would it be like a bracket, bracket colon, bracket comma, bracket colon, bracket bracket?
Whoa, you lost me after the 17th bracket. So A and then okay colon and then what do I do?
Open to,
Again open to?
or we could just do it with like colon, comma, colon, right?
Colon comma colon, right? Yeah. You want to try this?
Would we need the second set of brackets to keep the shape?
Brackets after this?
No, like within it.
Within it?
Yeah, because I'm just, I don't know if it'll keep the shape that way or if it'll just print.
Okay, so we can try this, and if you dig deeper into this, so it's saying for the array A, I want all the rows because that's what the colon is saying, and I want all the columns. So that's currently what we've got. And do you want to try this, or do you think that it's missing something and do you want to add something more to it and then try it?
I think that should be the same, but I'm not sure.
Yeah? Okay, we can try it if you're not sure. And yeah, it works. That's how you would get all the elements. Colon, because colon is saying everything in the row, and the second colon is saying everything in the column. So that is exactly how you would get the entire array again. Yeah, and if you were to just do the first colon as well, it would work. Yeah. And yeah, so the indexing in this case, it refers, it's called slicing. So now when I take the array A and I say A of 0 colon 2, what's being returned to me is a slice out of array A. And that slice is determined by what I pass inside the square brackets. In this case, I'm saying 0 colon 2. Now, since I haven't specified a comma and anything after that, it automatically treats it as me specifying 0 comma 2 along the rows, because that's the first dimension and I'm not passed in anything else. So it treats 0 comma 2 to be along the rows. So A of 0 comma 2 is essentially going to give me row 0 and row 1 out of my array A. So we can see that here. So X is the first two rows of the array A. And now what's cool about the slicing operator is it doesn't return a new array. It returns essentially a reference to that slice of the array. So now if I were to take this new array X, or not new array, this new array X, and change the first element of it to 100. So here x of 0, 0 is now 100, and let's print x. So now you can see in the array x, the first element has changed. Now, what do you think will happen to A? How many say A changed? And how many say A hasn't changed? Okay. Let's see what happens. A changes as well. And that's because, like I said, the slice operator, in this case the colon is acting as the slicing function. The slice that's returned to x is merely a reference to that section of the original array. So if I go ahead and start modifying x, I'm actually just modifying a reference, or it's actually just a reference to A. So whatever modifications I make to x are going to be reflected back onto A, which is why when I change the value of x 0, 0 to 100, it's actually A that's getting changed as well, because x is just a reference to A. So that's why A gets changed.
So how would you make just a copy of it?
Okay.
Like if you were to, instead of doing that.
Yeah. So there's the dot copy function, which returns a copy, and then you're good. And I've actually detailed that part later, because I faced quite a lot of trouble with some code because I forgot that you need to do this dot copy, and I will tell you about that when we come to it. Okay. Yeah, I have a bunch of questions now. I don't know why I gave away the cookie so early. Yeah. Okay. So anyone want to guess what will the output of this be? I mean, you can obviously try it out, but without trying it out, anyone want to guess what the output of this would be? Or just talk through what you think the output will be and why you think it will be that.
Can you show the matrix?
Oh yeah, sure. Whoops. Yeah.
Every other row along with columns 1, 3, and 4.
Okay. Anyone else with any different answer? Yeah.
Even rows for those columns in even rows.
Okay.
Even, I mean, 0.
Yeah. So that's what you said, right? Yeah. Okay. So this, yeah, same thing. Anyone else? Okay. Should we try it out? And in fact, that is correct. You get, so the colon 2 operator is saying start from 0, end with the end, and give me every second one. So the third, or the value after the second colon, represents the skip. So going from 0 to the end, skipping 2 items at a time, give me all the rows. And on the columns, I've passed in explicitly a list. So I'm saying I want only the first, third, and fourth column. So it takes every other row and gives me the first, third, and fourth column from that row, which is why I get the resulting array that we see here. Just to go into a little more detail about this colon, I could have, it essentially boils down to this. Colon 2 and 0 5 2 are the exact same thing. And that's how you can use the colon operator without specifying exact ranges. Now, if you wanted to make things slightly easier and do things in a slightly faster, more efficient way, if you knew that there was a particular way that you wanted to index through your array, and now this could be for some, if you're using certain complex mathematical functions and you need to, and if you have large matrices and then you need to extract elements in certain ways, you can use the numpy ix underscore function. And what that does is it takes the first argument you pass to it, which is in this case 0, 2. It looks at the first value in that, which is 0, and pairs it with everything you see in the second argument. In this case, that would mean 0, 0, 0, 2, 0, 3. Then it takes the second value in the first argument, which is 2, pairs it with everything in the second. So that gives you 2 0, 2 2 and 2 3 and returns that. So now when you take, this is essentially a slice into, or essentially what you would need to pass into the square brackets to return the elements at 0 0, 0 2, 0 3, 2 0, 2 2 and 2 3. And then when you take the output of this and pass it to matrix A, you get those exact elements. You'll get, this is 0 0, this is 0 2, this is 0 3, this is 2 0, 2 2 and 2 3. So what this is doing is, along the rows you have this array 0 comma 2, along the columns you have this array 0 2 3. It combines the two together in this sort of cross product manner, and then you're able to extract those elements directly from your array. This helps if you have much larger arrays and much larger sequences, and then you can index it using this numpy.ix function. So now I have an exercise for everyone to do, and it'll be based on the two things we just learned, which is broadcasting and indexing. And this is what you have to do. You have to add the two arrays together and then access the first and last element of every alternate row, and just someone tell me what I should type in, and then we'll see if the output is what it should be. Whenever anyone is ready, just raise your hand, and then I can type in what you say, and we'll check if it works or not. Anyone ready? Yeah.
A dot reshape 5, 5, 1 plus B.
Okay. Yeah, that works. Yeah, that works. Anyone else want to give it a shot? Yeah. Yeah.
Another way is a bracket colon comma np.newAxis.
Plus B. Yeah. Yeah, so this is a perfect example of how you could use np.newAxis. I mean, or you could also use reshape, but all of these things do the same thing, and the purpose of this was to show you that there are so many different options of how you can achieve all of this through NumPy, and whichever one works most conveniently for you, go for it, and you can unlock all of this power that NumPy has. Did anyone have any trouble with this? Does anyone want anyone to explain? Does anyone want any of these two to explain how they came up with this, or is everything all good? Okay, I'm going to assume everything is all good. Now, just to drive the point home that NumPy arrays are passed by reference, I've got the next bit of code ready. And that's because, so let me tell you, this one time I was working on this program at at work. I had to write code to generate a function that was able to give me Hilbert index values of coordinates. I was mapping a large numeric space into 2D Hilbert coordinates. And it was taking me a while for some reason to get this code working, and I kept wondering, I'm like, you know what, I've copied this off the internet, I've just switched my lists to NumPy arrays, there is no reason for this thing not to be working. And that's when I realized, I started debugging it, and then every time I passed my array into a function, and I looked at the array, I'd get the result, but then my original array would change, and I'd be like, wait a minute, why is this happening? I don't want my original array to change, I'm not doing anything to it, I'm just passing it to the function. Why am I seeing these weird things? Then I went into that function and looked at it. It was changing the incoming array and then returning something else completely different. And the reason it didn't matter before is because I was passing in a list. And the reason it mattered now is because I was passing in a NumPy array and it was passed by reference, which is why I was seeing all of these insidious things on the other side without realizing that on the internal side, it's modifying my array, and I wasn't cognizant of the fact that I should be passing in copies of my array and not references, because the first line of the function inside my array was an indexing operator, in which case it started returning slices and references, and then everything just propagated to the original array that I was using on the outside. So now, if you take this array A and I do B equal to A, and then I check whether B and A are the same thing, it's true. And then using NumPy, you can check whether they are actually physically the same thing or not by looking at whether they share memory. And they do share memory. So when you pass in, when you use the equal to operator to create a new, or do something like B equal to A, it is literally a reference you're passing. The same memory is being used for both of these arrays, which is why now if I do A of 1 is 100, it changes in B as well, because it's the same thing. But then if I do this, I say A equal to B dot copy, it returns the values of B to A and creates a new array. So then now when I do this, and I see the second value of A is changed to 9999, and then I look at what B is, B doesn't change. So in some cases you may want this pass by reference functionality, in some cases you may not. Yeah?
So the function you called that was generating the slices, it was assigning to the original values you passed in somehow, or was the function just buggy and misbehaving, or was it?
No, so I had passed in a NumPy array to it, and then let's call that parameter x now in the new function. It was directly indexing into x, so for example x of 1, and modifying that value. So when improperly written, because in the code that it was using, it was just a list, in which case it didn't matter at all. So it's not something that the author of the code is aware of. But when I switched it to a NumPy array, it was immediately noticeable to me that it was an incorrect implementation and that you should not be directly modifying that value. No, it was a completely non-NumPy related function that I was using. I was just passing a NumPy array into it, which is why I was seeing this behavior. And in the use case that the author was working on, that was not of any value to him, which is why this wasn't taken care of. But in some cases, you may also come across similar functions where it wasn't intended to be used with NumPy arrays, but you want the same functionality, and then you need to be careful that you're making sure that values or copies are passed instead of references when you need them. Another way to achieve the same functionality as b.copy is simply returning a slice of b, and that slice being the entire array. So b of colon. Then it basically says A is equal to everything in B, and then you can do the same thing, set one value of A as 999 and oops. Yeah, okay. Right, because B, sorry, my bad. So copy returns a copy of the array, so it's not a reference, so when you make changes to the original copy is not affected. But when you do the colon, then you're returning a slice, and slices are passed by reference, which is why when I modify an element in A, the slice or the reference, which is B, is also modified as well. So whenever you want to ensure, whenever you want to enforce pass by value behavior in NumPy, use .copy. Yeah.
Does NumPy keep the inherent property of the object passed into it? So for example, let's say we have a list, we have a variable that's a list. We create a NumPy array from that, and then we modify the list forward, right? Does that change?
So you're saying you have a Python list, you create a NumPy array using that list, and then you change the original array.
Yeah.
Then in that case, those changes are not propagated to NumPy because you've created a new NumPy array with the list passed into it, right? So for example, think of np.array as like a constructor. You pass in values to it. It takes those values, creates a NumPy array, and returns to you a new NumPy array, right?
So it's not pointing back to the original.
No, it's not pointing back. It's creating a new array, it's creating a new piece of memory, returning that to you. It's just taking the values from the list you've got, but it's not actually in some way, pointing to that same original list, and then those changes will not be seen further. Yeah. So this is an example using functions. So if I have this function which takes in an array, then uses the star equal to operator to multiply each element by 2 and return the array back. So here if I pass in a NumPy array to it, so the output y, that's all good, that's 20. But if you see the input that you passed in x, that also changes. And that's because inside the function, I've used the star equal to operator, and the star equal to does an in-place multiplication. So the actual reference that was passed in is multiplied in place, which is why you see that propagating on the outside. And this is not how you would want to write your function, but this is just an example of what could happen if a function was written this way because of these properties of NumPy. Now the same thing if you would write it in a better way, and you wrote your function like this, where you weren't using the in-place multiplication operator, you would still see the same result from y. Now the value of y is 20, which is why you now see 40. X remains 20 because array equal to array star 2, the array star 2 is returning a new array which is being returned to you. So the original is not being multiplied by 2 again because it's not an in-place operation that's taking place. The same thing doesn't happen when you use an integer. This is for NumPy arrays. In this case, you would see the same thing. X is 20. Yeah, so in this case, when I passed my array to func1, x changed as well. In this case, when I pass in an integer, the integer does not get modified even though I'm using the same in-place multiplication operator. So that happens with the NumPy array. Does anyone have any questions related to anything we've discussed so far? If not, I'll move on to the next notebook and some more NumPy features. Yeah.
So it's a NumPy question, it's a Python question. Can I get a list of variables that share memory? Because I want to raise warning.
You want a list of variables that
are sharing memory. Variables in the environment.
sorry?
A list of variables in the environment that are sharing memory. For example, A and B in your example, X and Y are sharing.
Yeah. So I'll just do A is equal to. So in this case now A and B share memory. You want a Python list of A and B, right? Okay.
Oh no. No, I don't want to.
Supposed to show anything that's sharing memory. Like, is there a function that
So
just
A and B are two variables, they are defined, right? But they are sharing memory. So there is one piece of memory, but two variables.
Yeah.
I want to get a list of variables that A
Oh, okay. So given,
Memory, then I can raise the warning message. If somebody changed B, I want to give a warning message that you also changed A.
oh, so you're saying if I know B, I want to basically have a function that tells me everything that shares memory with B? Oh, I don't know a NumPy function to do that. I don't know a Python function to do that. I'm not sure whether you can do that or not, but I mean, I'm happy to try it out later, and then if I find a way to do it, then I'm happy to share that with you. Currently, I don't know how to do that. Yeah, sorry. Anyone else? Yeah.
So for your exercise before, you also require to access the first and last element of every opening row.
Yeah.
Can you do that?
Sorry.
You ask to add the two arrays together. That's fine. And then
Oh, okay.
we access the element, the first and last element of every opening row.
Okay.
Can we do that?
Okay. So
So that's called C, right? So
okay. So now here, yeah. So I've put it in brackets. So now this is our resulting array where you add the two arrays together, and now over here we can enter now the logic to enter the first and last, get the first and last element of every row, right? So now why don't you tell me? Okay. So I put the comma here. So now from the left side of the comma, I would specify the logic I want for the rows, right? So now what should I put over here?
I thought we like colon 2.
Colon 2.
Yeah, to access every other row, right?
Okay. And
And then the next one will be 1 and minus 1 is a list.
what is in the list?
So 0 and minus 1.
0 and minus 1. Oh, I changed it. Oh, okay. Yeah. Oops. Yeah.
So I thought it should only have 2 elements per row, right? So let's get all the row here.
Okay.
Colon first, and then colon 2, and then you can put your list 0 and 1. You need 2 commas, because you have 3 dimensions.
What did you say? Colon 2?
So the first one is just colon to get everything.
Yeah.
And the second one is colon 2, and the third one is you can even do colon 2 to get every other one. So it's if you look at D, that should give you what you want.
Is this what you're expecting?
Yeah, the dimension seems to be a little bit strange, but
Well, I'll print out the dimensions. So the shape of A is originally 5, 5, and B is 5, 5, 3. So the first thing we need to do for these two to be broadcastable is, one, make both of them 3-dimensional. And now, so the third dimension of A should either be 3 or 1, right? And now, obviously, we can't artificially introduce it to 3. So using the np.new axis or a reshape, you would make that third dimension 1. Now the two can be added together. Now, the resulting array C has a shape 5 comma 5 comma 1. Yeah, 3, 5 comma 5 comma 3. Yeah. Then now, when you take this 5 comma 5 comma 3 array, you take every alternate row, right? And then the first and last column within what you've selected. So now, for the first dimension, you say, give me everything. And then the next dimension, if you take the last 2 dimensions to be the row and column that I'm talking about, or you can choose to have the first 2 dimensions of the row and column that I'm talking about, whichever one. So for this case now, let's say out of my 3 dimensions, I'm saying the second dimension is rows and the third dimension is column. Now give me every alternate row. So on the second dimension, give me every alternate one, which is colon colon 2. So start to end, skipping 2 in between. On the last dimension, I want just the first and the last, right? But in this case, it's 3. So saying alternate is the same. Or I could do yeah, 0 and 2. Oh, it's 4. Oh, shit. Whoa, okay. So I have half an hour left, right? Cool. Okay, so if anyone has any other questions, we can just take it offline. Actually, I wanted to go through this other notebook. First one went longer than I expected to. So universal functions, stride tricks, and Einstein summation are 3 really cool features in NumPy. And so I'm going to quickly go through the universal functions and then move on to stride tricks. And then if we have time, Einsum. Einsum is really cool. So if we don't get time to do it, I'm super happy to talk to you guys about it afterwards, because I just think Einsum is really cool. So here we have an example of creating NumPy lists using the arange function, or actually doing it using a Python list. So here, using numpy.arange, I can create a 100,000 list array in 1.04 milliseconds. And if I did the same thing using Python, it would take me 5.2 milliseconds. So this is just to highlight how NumPy functions are just inherently faster than doing things the Pythonic way. You got the same thing for sum. If I wanted to sum up all the elements in my NumPy array, I could use the universal function np.sum. It takes 462 microseconds to do that. Now, as I said before, loops are not your friend, and here I will show you why. If I did the same thing, if I want to sum up this 100,000 element array using a for loop, it takes 19 milliseconds to do. That's an entire order of magnitude slower than using NumPy functions to do it. The same for average. You got 443 microseconds and 45 milliseconds. If you wanted to use the abs function, this is interesting. If you take these 2 cases over here, if you take these 2 functions over here, if I just use Python's abs on a normal integer versus NumPy abs on a, sorry, not integer, on a float, Python abs versus NumPy abs, the Python abs is faster. Now, if I take the Python abs and do it on a list of this size, so that's 500 elements, versus NumPy abs on the same exact list, what do you think would be faster, Python or NumPy? Okay. Python is faster. Now, this example, take a Python array and then using a Pythonic way, using the Python abs function, create a new array of absolutes, or use np.abs on this array. Which one do you think will be faster, NumPy or Python? Okay. And yeah, NumPy is faster. It's 26.9 microseconds, and doing it in Python is 153 microseconds. So the numpy.abs function works better on NumPy arrays, not on any array in general. Now, okay, now I'm excited. Now this is my favorite, stride tricks. You just want to get through the previous stuff. With stride tricks, it's a really neat way to do things like create a sliding window out of an array, and just do more complex indexing. Now I'm sure, I don't know, have many of you had to create sliding windows or similar things, and ideally what you would do is if you're doing it in like C or C++ or something, or just pure Python, you would use loops and a whole bunch of other stuff to get appropriate sliding windows. What you can do with NumPy is you can create strides, which essentially will return a reference to your array, and it will stride through it in whichever way you need to return whatever sort of sliding window type function you want. So in this case, first I'll show you the, okay. So now let's say for this array of numbers from 0 to 9, I want a window of size 4, and I want to jump by 2 elements each time. So that means I'd want my output to be 0, 1, 2, 3, 2, 3, 4, 5, 4, 5, 6, 7, and 6, 7, 8, 9. So I want windows of 4 and jumps of 2. Now in this one line function, I can do that, and this is half of it. So the first thing to do with stride tricks is you basically stride it with a window, with a step of 1 at each time. So now you first define the window. So here I've got my window taken care of. I've divided my array into windows of 4, 0, 1, 2, 3, 1, 2, 3, 4, 4, 5, 6, 7, and whatever. And now I want my stride to be 2, so I want every alternate one. So then using the : s, I can get every alternate one out of that, and then I'm left with 0, 1, 2, 3, 4, 2, 3, 4, 5, 4, 5, 6, 7, and 6, 7, 8, 9. So here in one line, you are able to stride over your NumPy array and get this result. And what's awesome about this is it's super fast, and this is not returning or creating any new memory. This is purely done in reference. There's no new memory created over here. And this is how a NumPy array is stored in memory. It's essentially it's a C structure. It's got a pointer to the data that the array is representing. It has a descriptor of the data. It knows how many dimensions the array has. It knows how to stride over the array, and it has a base, it has flags, and it has a reference list. So now if you were to, so for example, if you looked at this array X that I just created, an array range of 10, and you looked at the array interface, you would see that this is the pointer to the data that the array is representing. Now if I do stride tricks over that to get this sort of, this new array, which is 0, 1, 1, 2, 3, 4, and I check out what the array interface is, I see the exact same, yeah. So you have the exact same memory being pointed to by both X and Y, despite me having done this stride tricks. So it just in memory alters the strides. So here you can see the strides are none and the shape is 10. Here the shape is 9, 2 and the strides are 8 by 8. So it's just changed these descriptors around how Python is reading these arrays out of memory so that it's read in this new shape. So what strides is doing is, if you see in this case over here, strides is 8, 8. So what it's telling you is my new resultant array has a shape of 9, 2. On the first dimension, which is 9, my stride is 8. So if you look at this, the first row of this array is 0, 1, and the second row is 1, 0. So now when you go from the first element of the first row to the first element of the second row, so you've moved 1 along dimension 1, right? So from 0 to 1, in memory, how much have you strided? You've strided 1 byte, you strided, one byte, or 8 bytes, sorry, and that's because in the original array X, between 0 and 1, it's 1 float offset, right? You go 1 float from 0 and you reach 1. So in memory, it's linearly laid out. So that descriptor is just telling you, or just telling Python how to read from memory into this array so that it's able to do it such that I receive now a 2-dimensional array with 9 rows and 2 columns, and it's 0, 1, 1, 2, 3, 4 and so on. And on the second dimension, the stride is also 8, and that's because if you go one element over the second dimension, you're going from 0 to 1, and again, as we see over here, to go from 0 to 1, it's one jump. So which is why it's 8. So 8 in this case is the size of float, and that depends on the system you're using. It could be 4, it could be 8. And then now, when you go one more on the first dimension, you go from 1 to 2. Again, that's an 8-byte jump. Again, you can see over here, 1 to 2 is an 8-byte jump. So NumPy.stridetricks is giving you this functionality of creating complex arrays like this from a simple base array, but doing it with the speed of something like a reshape or something like a transpose, because it's actually not manipulating data, it's not creating a new array, it's not copying data anywhere, it's just changing those two fields, it's just changing shape and it's just changing strides in the C structure representing that array. So when Python reads this array and it sees that C structure, it knows how to stride over this piece of memory so that you're able to see the array, or that you get a view of the array the way you want it to. So it's just changing the underlying structure, which is why using a function like stridetricks is a lot faster, a lot more efficient than actually creating a new array by looping or by whatever other methodology you would want to use. Yeah?
Stridetricks is just part of the NumPy internal data structure. Is that exported from the module?
Yeah, stridetricks is it's a NumPy library function that you can use. This is the syntax, numpy.lib.stridetricks. So it's exposed to you, you can use it, yeah. So everyone understood stridetricks, because otherwise I can either go into a little more detail with another example, or I can briefly touch upon Einstein summation. So whatever you prefer. Anyone want to go into a little more detail on stridetricks, or everyone wants to do Einstein summation? Okay. So another cool thing in NumPy is Einsum, and so Einsum in a lot of cases is really useful because it's faster than doing stuff in normal NumPy and Python. In a few cases, for example, like the dot product, NumPy is just like heavily optimized. The dot product is like optimization on steroids, so nothing's going to beat that, but that's one of those few functions that are really written down core in BLAS or Fortran, so they're really fast. But for a lot of other functions, using Einsum is faster than using a normal NumPy function. So here, the syntax is a little tricky. So for example, if I have these two arrays A and B, so now both of these are 2-dimensional arrays of size 3, 3. Now, with Einsum, you have two or more arguments that you pass to it. The first argument is a string, and the string is what defines the function that should take place now with this Einstein summation. So the syntax you would use is like this. So you have this arrow operator. On the left-hand side of the arrow operator, you define the dimensions of the input. On the right-hand side of the arrow operator, you define the dimensions of the output. So here in this case, I'm passing in the array A to it. A has 2 dimensions, and convention is you start with the first dimension being named as A, and then you go I, J, K, so on. Doesn't have to be, it's just convention. So now here I've said my input array has 2 dimensions. The first dimension is I, the second dimension is labeled as J. There's only one, so there's nothing else on the left-hand side of the arrow. On the right-hand side, I've left it blank. When you leave it blank, in this case, it simply translates to replicate the input on the output side. And what this does is just returns the entire matrix as it is. which is the same as doing a dot view or a of colon or the same thing. So this isn't really a cool example of Einsum. This is just to show you that on the left hand side you have the inputs, on the right hand side you have the output. Now what you can do over here is say, okay fine, my inputs are ij, my inputs are these 2 dimensions, but on my output I want only 1 dimension. And here it returns 3, 6 and 15. So when I leave a dimension out of the output, it tells me that I want to sum along that dimension. So here my input is I comma j, so that's dimension 0, dimension 1. My output is just I, so that's dimension 0. I've left out dimension 1, so it tells me, okay, for the input array that has 2 dimensions, my output array should have only 1 dimension and it should be summed along dimension 0. So leaving out something on the right hand side of Einsum indicates summation to happen along that dimension. So in this case, when I've done I comma j, ij on the left hand side and just I on the right side, it sums it along the dimension j, which is axis 1, which is why the resultant array is 3, 6 and 15. Now if you were to do the same thing, in this case I say my input is ij and my output should be ji. It is me telling Einsum that I want the transpose. So my input has the dimension I and j. My output also has 2 dimensions, but the first is j and the second is I. So it's taking the dimension, it's taking I and j from the left hand side of which is the input and reversing them and giving me the output. So it's doing a transpose of my matrix using this Einstein notation. Now as I showed you that extremely elegant way earlier to get the diagonal of a matrix using the 2 lists as rows and columns, you can do the same thing using Einstein summation. So here my left hand side is just I and I. So now I know it's 2 dimensions because I've passed in 2 characters on the left hand side, but I've labeled both of them as I. So I'm saying on my input I want the 2 dimensions where I want equality between the 2 dimensions. So and on the right hand side I only want to see 1 value. So I want my right hand side to be 1 dimensional. And here it returns the diagonal of the matrix, which is the same as using numpy.diag, but you can see here this is one of the cases where Einstein summation is faster than using a normal numpy function. And all of these cases are great when the examples are small, but the true power comes in when you use much larger arrays. Then you're actually able to see noticeable differences in times taken using normal numpy functions and using functions like what I've shown you here with the Einsum. You can do the same thing with the trace of the matrix. So here on the right hand side of this case I've said give me back 1 dimension, I've said give me back 1 dimension, which is why I've received this 1, 2, 5. Here this is the same as doing this, which is saying on my input I have 2 dimensions and on my output I have nothing, so sum it along that, which is why the 1, 2, 5 is summed to give me 8. So anytime you exclude something on the right hand side, you are saying sum along the dimension that you just excluded, which is why you're able to get the trace of the matrix in this way. So now here this is an example of using Einstein summation for matrix multiplication, and this is where you'll really understand the syntax in more detail. So here I have my 2 matrices A and B. This is the matrix multiplication of the 2. Now when I use Einstein summation notation to represent this, I now on the left hand side of the arrow need to pass in the dimensions for both the arrays because I'm passing 2 arrays to this function. So I'm saying my first array is defined with the dimensions I comma j. My second is defined by, again, I comma j, and my output should be I comma j. So what this does is, anytime you have the same variables or the same letter used to denote dimensions of a matrix on the left hand side, you are telling Einstein's summation to multiply those dimensions together. So here I have I and j for array A, I have I and j for array B as well. Now both I and j are repeated and they're used to represent both these arrays. So what you're telling Einsum is multiply the two together, because dimension 1 is I in A, dimension 1 is I in B, dimension 2 is j in A, dimension 2 is j in B. Now because I've repeated the notation I've used, it means I'm indicating to Einsum that I want multiplication to happen along those two. And my output is again ij, which means I don't want any summation to happen, so just return everything as it is. And it multiplies element by element, each element from A and each element of B, and returns that array to me.
So it is element-wise.
Element-wise multiplication, yeah. And now traditional matrix multiplication is shown over here. So now in matrix multiplication, you multiply the rows of the first matrix with the columns of the second matrix, right? And then you add that together and that becomes the element or the output at that particular location, and you do that for the whole array. So now for array A, I've called it I comma j. So my rows are I and my columns are j. For array B, I've called my rows as j and my row wise as j and column wise as k. So now the columns of A, which means if you go from left to right on A and if you go from top to bottom on B, are both represented by the same letter, j in this case, which means you want multiplication to happen between those two dimensions. And on my output, I've left out j, which means I want addition to happen along that dimension as well, and I want the other two dimensions to be what the shape of my output is. So you know when you have matrix multiplication, you have the rows and columns. The columns of the first and the rows of the second should be equal, and the output is the rows of the first and the columns of the second, right? So here you have I comma j and j comma k as what's defining the dimensions of the input. So here you have the columns of the first and the rows of the second as equal, because both are j, and the output dimensions are I and k, which is the rows of the first and the columns of the second. And then when you run this and you multiply it, you see that you get the matrix, or the traditional matrix multiplication of these two elements. So in having something in common on the left indicates multiplication between these two, and excluding something on the right means addition along that axis. And just to give you an indication of how fast this is. So here the NumPy dot function is faster, and that's because dot is written in, I think it's written in BLAS. So dot is one of those functions that you will not find, I do not think you will find any other function in NumPy to replace dot that will be faster than dot. So that's using Einsum. And now this example over here, how much time do I have left? Okay, so I think I can quickly go through this example. So this is an example that does convolution of two matrices using stride tricks and Einsum. Does everyone know what convolution is? This GIF sort of shows how convolution works. So the lower matrix, the larger one, is, for example, matrix A, and the smaller matrix on top, which is this one over here, is called the kernel. So what you do with convolution is you take the kernel and you multiply each subsection of the larger array with that kernel, and then you can apply any function you want to it. You can add all of them together and have that as your output, and you slide that kernel along the larger original matrix to retrieve whatever output you want, and that process is called convolution. Now to do that using NumPy, I create the larger matrix A, which is 0 to 24 in the shape 5, 5. I create a filter or my kernel of shape 3 comma 3, and these are the values I've given it. Now I want to multiply this 3 by 3 kernel over all 3 by 3 submatrices from my larger 5 by 5 matrix. Now how would you do that if you can't loop? You would probably need to create all of those 3 by 3 submatrices, multiply the larger matrix with it, and then add them together so you get your final output. What you can do using stride tricks is create a reference to that larger matrix that strides over it such that the resulting shape is all of those sub 3 by 3 matrices, and then you multiply the kernel over each of them. So here what I've done is I've defined, so now if you take a 5 by 5 array and you want to multiply 3 by 3 matrices over each of them, you would have one like this, 2, 3. You would have three submatrices along each column. You would have 3 submatrices along each row. Each of those submatrices would have 3 rows and 3 columns. So the final resultant array of subarrays that you should get from stride tricks would be of dimension 3 by 3 by 3 by 3. So that's what I've created over here. Just define the shape and define the strides that I need to take. So the shape is 3 by 3 by 3 by 3, and the strides I've defined is 40 by 8, 40 by 8, and I'll explain why. So here if you look at the submatrices, these are the submatrices that have been created. So you look at the original, now the first submatrix is 0, 1, 2, 5, 6, 7, 10, 11, 12, then 1, 2, 3, 6, 7, 8, 11, 12, 13, and so on. Now the first dimension of strides was 40. Now you look at the first element over here, which is 0, or let's print that out. Okay, now this is the first element of the, this is basically element 0, 0, 0, 0. Now if I want to check what the stride should be along dimension 1, let me look at what value is there, what value would I get if I move by 1 dimension along the first dimension, by 1 value along the first dimension, and that is 5. Now in my original matrix, from 0 to 5, how many jumps are there? I go 1, 2, 3, 4, and 5. I have to jump 5 times on my original array to get the first jump of the first dimension of my resultant submatrix array, right? So now 5 jumps of floats in this case is a stride of 40, which is why the first element over here is 40. Now if I want to find what the strides of my second dimension should be, let me see what value I get. Again this is 0, and if I move by 1 along the second dimension, I get 1. Now if you look at the original array, to go from 0 to 1, the jump is 8, which is why the strides on the second dimension is 8. Now I do the same thing for the third, it's 0, and if I jump by 1, it's 5 again, which means now the stride along the third dimension is again 40. And again 0 to 1, it's 1, so the stride along the last dimension is 8, which is why the resultant strides are 48, 48. And now I create those submatrices. I've created those submatrices already, and these are the submatrices. And now I need to multiply each of these submatrices, which are convolution filters. I need to multiply the convolution filter with each of these submatrices and then sum them up together. So each 3 by 3 matrix is multiplied with the 3 by 3 filter, multiplied together, summed up to give one value, and that is the value that is in my final output. So to do that, I use this Einstein summation. So on my first array, the conv filter, it's 2-dimensional, so I define the dimensions as I and j. The second array, the submatrices, are 4-dimensional, right? It's 3 by 3 by 3 by 3. So I call those I, j, k, l. Now here I and j are common between conv filter and submatrices. That means I want the entire conv filter matrix to be multiplied with the first 2 dimensions of the submatrices, which means each 3 by 3 matrix will be multiplied with the convolution filter. I've excluded INJ from the output, which means INJ should be summed up, which is essentially taking the 3 by 3 conv filter, the 3 by 3 submatrix, multiplying it together, adding up all the elements into it, and then my final output should only have the dimensions K and L, which is in this case 3 by 3, but the first 2 dimensions are being multiplied with each other. And he tells me that I have no time left, so I'll end with this, and you can see the output over here, and this is the resultant output you get. I understand that I had to hurry up through the last bits. The first notebook took a little longer than expected, but I am more than happy to talk to you in more detail about Einsum, stride tricks, ufuncs, or any of the other stuff I've talked about, because these are all really cool functions and things I really use a lot, and I think will be very beneficial if you use them as well. So more than happy to talk to you about that offline. Other than that, thank you. I hope you liked whatever I spoke about, and I hope you found some of this at least useful and will use this in your work later on. Thanks.